All righty, gonna wrap up complex numbers today. So just a quick recap. 2-4 was we started talking about complex numbers, which are really the with a real part and an imaginary part. And the idea is you get an imaginary number anytime you take a square root of a negative. So the official rule is the square root of -1 can always be rewritten as I. So anytime you have that happening, that's going to create what we call an imaginary number, which is a part of a complex number. So it sounds real weird, but mostly we're looking at how do you work with these things. And so yesterday we went through how to add, subtract, and multiply. And hopefully those weren't too bad for you. The rules are pretty simple. They're kind of just your normal algebra rules, and then simplifying from there. So today we're going to talk about how do you divide or do a quotient. So we're going to introduce this concept called a complex conjugate. And complex conjugate are two complex numbers with the same real part and opposite imaginary parts. So what that means is it means they're going to have the same real part, the A part, but their BI part, one's going to be positive, one's going to be negative. So like an example of this would be if you had like 6 plus 3i, and the complex conjugate of that would be 6 minus 3i. And so we actually saw this in some of our multiplication problems yesterday. So like this right here, this is an example of a conjugate pair. And this one here is also an example of a conjugate pair. And the special thing about a conjugate pair, which is actually why we did these two examples yesterday, is they make the imaginary part cancel out every time. You'll notice anytime we did one of these where it was an opposite imaginary part, it ended up being just a real number answer. Same thing here. This ended up being just a real number answer. That's actually pretty valuable because that's how we're going to do these division problems. So this says, how do you write this quotient in the form a plus bi? So this is saying take 10 and divide it by 2 minus I. Well, what happens here is if you have a real number and you try to divide it by a complex number, you can't like really do that. You can't take something and divide it by something that's not of the same number set. So what we do instead is we use these conjugates to rewrite it. So the move for this, while you're not technically doing the division, you're rewriting this so it looks better. Basically, it's going to be in this form as opposed to being in a fraction form. So what we do is we take the problem, whatever they give it, whatever it is, and what you do is you multiply it by whatever the conjugate of this denominator is. So the conjugate of this would be 2 plus I. And so we multiply it by 2 plus I over 2 plus I. So this is a move where technically we're just multiplying by 1, because that's what this is. This is something over itself is just 1. So it's not going to change the value of this at all, but it's going to change how it looks, and it's going to make it look the format of what we want. So you'll see what I mean as we work it through. All right, so what we do is this is going to be the distributive property. So we're going to distribute here and here. So that's going to be 20 and then plus 10i. That part's pretty easy. In our denominator, I like to put the parentheses on here. You can do it here too. But this is going to be your distributive property or your FOIL. So let's work it out. You're going to get 4. You're going to get plus 2i. You're going to get minus 2i. And you're going to get minus I squared. And what you're going to notice as you do some of these, you're going to notice the same kind of thing happens every time. These imaginary parts will always be opposite. And then this, you're always going to end up with an I squared here, which we've learned I squared is just -1. So what's really going on here? This is 4 minus -1, which is just 4 plus 1. So what we have is top part hasn't changed yet, but this bottom part's just 5. And now you probably see, okay, this is how this is going to be in this format because these are both just divisible by 5. So we can just rewrite this in a nice simple form. 20 divided by 5 is 4, and 10 divided by 5 is going to leave you with 2i. And so what this does for us is it simplifies that problem. It takes what was a division problem, and by using this little conjugate, kind of a trick here, kind of just a move really, but what it does is it lets you rearrange the problem. So we don't actually do the division because we can't, but we manipulate some things and we change the form of it. So now it is in simplified form. So yes, you're like doing the division, but instead of actually trying to work it out, you use this conjugate to simplify the problem in a little bit different way. And so that's that. So there's a couple try it ones here. So if you want to take a second, pause it, see if you can figure those out, and I'll work them out too. Okay, so I've worked through the first one here. Just to kind of walk through it, I took the conjugate of the denominator, so 2 plus 6i, 2 plus 6i, and then I went through and I distributed everything. So 80 times the 2 and the 6i gave me this. Here, 2 times 2 is 4, and then I got 12i minus 12i, and minus 36i squared. Again, these are always going to be opposites because that's how the conjugates work. And then this I rewrote as a negative 1, so this became plus 36, which gave me a 40 in my denominator. And then I just divided each of these numbers by 40, and it comes out pretty clean. You get 4 plus 12i. So now, same thing with the B one. Let's work it out. All right, so same kind of deal with this one. This one actually is a little bit tougher because the numerator is a complex number also. Like in the other ones we looked at, it was real. So the reason it gets tougher is you get more terms in the top here. So again, we distribute times all of the conjugate here, which again, you just change this sign. So it's negative 1 minus 2i. That's what I had here and here. And then I distribute all these parts out, which is why I got 4 terms on the top and then also 4 terms on the bottom. Your I squareds are always negative 1s. So I went ahead and kind of marked those. These two imaginary numbers canceled out, but these two didn't because these top parts are not conjugates of each other. So I end up getting an imaginary part up top. So I had this piece is negative 6, so I ended up with negative 10. And then the negative 8 plus the 3 gave me a minus 5i. And down here with the 1 and the plus 4 ends up being just 5. Once you're here, the problem simplifies really nicely because these both just divide by 5 and you get negative 2 over a negative 1i, or just negative I. So a little tough on those. This is, I think, the toughest move for sure is these division problems because they do take a little more work, a lot harder than the adding or subtracting or even multiplying. So that's those. So if we jump on to example 5 here, it says, how to use complex numbers to factor the sum of 2 squares. So if you remember, we talked about difference of squares the other day. Sum of squares is kind of another rule. And what sum of squares is the only way you can ever make this happen is if you use imaginary factors, okay? So the answer to this is what is this factor to? So if you have variables, kind of just setting up the format to it. Anytime you have something squared plus something squared, it's always going to factor to x plus yi and x minus yi. So it's kind of like, just to talk about sort of a side problem real quick, if you remember difference of squares from the other day. So when we had this was a square minus a square. This always factored to like x plus 4 and x minus 4. But now they're saying, okay, instead of this being a minus sign, what happens when it's a plus? All that changes is it's going to factor exactly like this, but you're going to put an I on those two terms. So what you're going to see here is this actually isn't too bad at all. So now it says, how do you factor this? So this is a sum problem, but if you notice, these aren't perfect squares right off the bat. However, you can pull a GCF out of these. So if you pull a 3 out of this to start, you pull 3 out, and now you have 4x squared plus 1. Now this is a sum of squares because this is 2 squared and that's 1 squared. So from here, now you can look at this and be like, okay, so sum of squares, this is going to have to be a 2x plus 1i and a 2x minus 1i. And so it's really just a shortcut. Could you do it using like your AC factoring? Yes, you could, but it gets really kind of nasty, and I personally would not recommend doing it. I would definitely go this route to be able to factor these sum of squares problem. Basically recognizing it's okay, it's just going to be whatever the roots of these two parts are, one set positive, one set negative. In other words, they're always going to be conjugates of each other. So to use that term from today. So here's an easy one. This one, they're already both perfect squares. So this is going to be 2x plus 5i, 2x minus 5i. And you could flip-flop the plus and minus parts. It doesn't matter which one comes first. I usually just put the plus first, but it really doesn't matter. This one is a lot like this B example. We take a GCF out first. So it looks like these would be divisible by 2. So we pull that 2 out, leaves you with 4y squared plus 9. Now those are perfect squares, and so we can use our sum of squares rule here. So that's going to be 2y plus 3i and 2y minus 3i. Okay? So that's how sum of squares works. It's just like difference of squares, with the exception of, because it's positive, the only way you can make that happen is by putting i's on both these numbers. All right, so now they throw in just the last part of this is now using that to also solve the problem, which is actually pretty easy because once you get it in factored form, you just use your zero product property. So like in this case, it says solve this using factoring. All right, so if we factor this, once again, it's a sum of squares. So it's going to be x plus 2i, x minus 2i equal to 0. So now we look at that and we realize, okay, what's going to make those equal 0? Well, they are going to be imaginary solutions. So to make this part equal 0, x would be a negative 2i. And to make this equal 0, x would be a positive 2i. So those would be our two solutions. So this is an example of a problem that has two imaginary solutions, which you might think sounds really, really weird, but actually here's why. So we've already solved the problem. We've already answered this, but let me show you like why they're imaginary. Think about what this looks like if you were to graph it. This is an x squared shifted up 4. So the graph of this looks like this. And so the question of when does this graph ever equal 0? Well, the answer is there's no real number that ever does this. So before today, really, you would have answered this as this problem has no solutions. Technically, this problem has no real solutions. It does, however, have two imaginary solutions that you can find through factoring, which again, sounds super weird. And this whole concept of imaginary numbers is a really minor thing. It's not one of the like most important ideas in all of Algebra 2 or anything like that. It's got a few real-world applications. It's used in some electronic engineering because it allows currents to flip back and forth. It's also used in some programming. But again, this is a pretty minor thing. It's kind of weird. It doesn't come up a ton, so just kind of laying that out for you. But the idea is these problems should not be very difficult because, once again, this is the same idea. It says solve this using factoring. So we're going to factor this sum of squares. So it's going to be x plus 7i, x minus 7i. And then your solution should be pretty obvious. Negative 7i is going to make this one 0, and positive 7i is going to make this one 0. So those would be our two solutions. And if you'd rather write it as like plus or minus 7i, that's perfectly fine too. So you can write it as, these are my two solutions, or you can say, this is my two solutions. Those mean the same thing. Either way is perfectly okay. Once again, same exact idea right here. So these are both perfect squares. So it's going to be 3x plus 5i and 3x minus 5i. Now remember here, if you ever look at this and you're like not sure how to solve this, like maybe you don't see right away, like which you might not because they're measured numbers, might feel a little weird. Just take this and set it equal to 0. So 3x plus 5i needs to be 0 and solve it for x. So minus the 5i. So now you have 3x equals negative 5i and divide by 3. Oh, so it's just 5/3 I. So your answers are going to be, negative 5/3 I. So you're going to get negative 5/3 I and positive 5/3 I. So I would just answer it like this. And that's going to be your easiest way to answer that type of question. Because you do know that these are just going to be opposites of each other because they always will be with these conjugate pairs. So once you find one of them, the other one's just the opposite sign. And that's pretty much it. So we'll have you try out the OTI today and see how it goes.